Yeah, so I'm going to talk about the verifiability vision. So the idea is that we want to verify the full digital world. And I think it's something that resonates with many of you, right? This is also what we hope for in the blockchain world, that we can create sort of like very trustworthy data that people can rely on. So this slide here is sort of like the very short summary of what is the verifiability vision. Alessandro Chiesa and Aaron Troma in 2010 introduced the notion of proof-carrying data. So the idea is that you have data, and data comes with a proof of correctness. And whenever you compute a new piece of data, you sort of like take verified data, check their proofs of correctness, and then you know that you're relying on verifiable data. You can now compute your new piece of data, and you can create a proof that this computation is correct, right? And that proof would both show that you computed correctly, but it will also show that, well, all the previous data, the inputs you had, were also provably correct, right? So you have this recursive composition of proofs that means that the whole graph of data that you're computing is verifiable. Okay, so what are examples of things that we would want to claim about data, right? So imagine you're reading your online news site, right? You may see an image, and it would be nice to know that this is actually a correct image, not some fake information. And nowadays, there are some cameras that sign the data, sign so like what are the GPS coordinates, what is the time, and so forth, right? So as an witness to this being a correct image, you may imagine that using the raw data from this camera and the GPS coordinates and the signature and so forth, right? And then the proof might demonstrate that, you know, this 100 kilobyte image that you're looking at is actually derived from a much bigger set of raw data with these kind of meta information associated with it. Other examples, if you are building online voting systems, you may encrypt votes for privacy, right? But then, you know, these systems can get messed up if somebody submits an invalid vote. So there you may have proofs that the encrypted vote is valid. And here it's actually important to have confidentiality, right? That you don't want to leak anybody's vote. You just want to make sure that they're actually casting a valid vote. So like the poster child example that we use for zero knowledge proofs is that identification purpose, right, where a customer wants to prove they're over 18 years old, and people are now sort of like actively going out and getting data from, say, passport chips or something like that, so you have some raw material to work with to give these kind of proofs. And in the blockchain world, there's a lot of applications, right? So for instance, you may want to prove something about a smart contract execution. Okay, so let me sort of like generalize that a little, right? So cryptographers, they then think about this as a class of statements, okay? And talk about proof system for these class of statements. And there we have typically a setup that we expect to be publicly available to all parties. Sometimes there's some trust assumption in that, so there may, for instance, be a ceremony in which you could create that. But if that is once that is done, then it's there and available to everybody. And then you specify a proof algorithm, a verify algorithm. The proof algorithm would take the prover key, the statement you want to prove, and potentially a witness, if there's such a thing, to this statement being true, and produce a proof. And the verifier, conversely, would take the verification key, the statement, and the proof, right? And then either accept or reject. And this was invented back in the 80s, where the definition was that it should be complete. So if it's a true statement, then the prover has a witness, it should be possible to create a proof. And conversely, if it's a false statement, then it should be infeasible to create a proof. And then the twist in the story back then was that, well, it turns out the proofs can actually convey that, well, this is a true statement without conveying any other information, right, which is very surprising. So the zero knowledge property is that, well, the proof reveals nothing about the witness. It just gives you one bit of information, namely that the statement is true. So it's this kind of proofs that we would want to give for the data that we want to verify. What I want to talk about today are what I see as challenges for proof-carrying data to really take off. So like 4 aspects of that I want to talk about: the versatility and ease of use of these proofs, the cost that comes with them to create them, composability, right? Because the idea of proof-carrying data is that you actually compose proofs. You would have like inputs, and they have some proofs, and you want then to compute new data and give proofs for those, and so you have to have some composability of the proofs. And then I'll talk a bit about the trust anchors. How do we link these proofs to real-world data? Okay, so this is like a bit of a history of like, how did people go about sort of like ease of use for developers in the olden days. And this is an old picture of me. I did my PhD work working on voting systems where you needed to create proofs of valid votes. And back in the day, the way you construct a proof system is that you hire a cryptographer and then they construct a special purpose proof system for you. And then in the recent years, there's been a lot of exploration of building tools that make it easier to construct proof. So something we could dub as sort of like the ASIC approach is that you have a program, you want to prove that inputs to that program yield a certain output. Well, let's compile the program into a proof system that can handle that. And more recently, there's a lot of teams now working on ZKVMs, where this is sort of like giving you a more traditional experience of proving something. So the idea is that you take a program, you compile it down to something that the VM can execute, and then the VM takes this executable file, the program P, some inputs, and produces an output, and together with that, a proof that the computation was correct. So let's dig a little more into what does that look like? So ZKVM takes as input a program. At Nexus, we're using RISC-V as the target programming language, but there are also many teams building ZKVM, so you could also find this for WASM or special purposes languages like Cairo and so forth. Then the program can take an input X. They may also take a witness W, and it will produce an output Y, and then a proof pi that this output is correct. And there will be a matching verify algorithm that then looks at the program and the inputs X and the output Y and the proof and decides whether it accepts this proof as being correct. And the whole goal for all these teams that are building ZKVMs is to give a very easy developer experience, right? So the way it will look like for a developer is something like this. You can just use a command line and you can prove or verify these computations. So I think we're getting somewhere with sort of like the ease of use from a developer perspective. The next thing, the next barrier, I think, is the cost. So let's sort of like dig into where we are right now. And I think the whole community has settled that the type of proof that you want is a snark. Okay, and what is a snark? Well, it's one of these proof systems where we want the proof to be succinct. Okay, so the succinctness property is that the proof is really small. Okay, and we're talking about, in the best cases, something like a couple of 100 bytes. Okay. And the interesting thing is that it can be a couple of 100 bytes regardless of how complex the statement is, right? So imagine you have a program, it does like lots and lots of operations, but you still just get a very small proof and something that's very easy to verify. We want the proof to be non-interactive. And to give a little bit of context, because that's not present on the slide here. So in the olden days, when people were thinking about zero-knowledge proof, they were thinking about proofs where you had an interaction, where the verifier was interrogating the prover. But the nice thing, if it can be non-interactive, where the prover just produces the proof and then it's done, is that now you can take these proofs and you can copy them and you can distribute them, right? So if you see a proof for some claim, then you can just make a copy and you can send it to somebody else and they will be convinced as well. And then we want it to be an argument of knowledge, which is sort of like a technical way of saying that the only way you can construct a proof is if you were also able to construct a witness. So in other words, you ensure that it is a true statement. Okay. So when we have succinct proofs, right, then we have these very small proofs, and the verification time is really small as well. It's independent of the program execution time. It's also independent. The verifier does not take this auxiliary witness as input, right? And that's super cool, right? Because it means verification can be much cheaper than doing the computation itself. And I think this is like a key message here, right? That verification is cheap, okay? And that's what sort of like makes the verifiability vision possible, right? In some sense, all these data that come around with proofs, right? The proofs are for free, right? So it's sort of like from a user perspective, okay, I can get a piece of data and blindly trust it. Or I can, at exactly the same cost, almost, get the data and the proof that it's correct, right? Which one do I prefer? Well, if it's for free, I would want it to be verifiable. Okay, so where are we today? Proof size is really small. It can be as low as a couple of 100 bytes. The verification time is really low as well. It can be as small as just essentially reading the statement. What is the bottleneck nowadays is the proving time, and that's horrendous, right? So the overhead of like, you know, the cost to prove something versus you just compute it directly it's like many orders of magnitude. There's a lot of work going on to improve that, right? And if you sort of like look across time, right? Like back in the 80s when zero-knowledge proofs were invented, people didn't even think about like the efficiency of the prover. It could have infinite time to prove something. And people have become more and more careful. And I think now we're sort of like, you know, the way you measure it is you would talk about like, you know, how many cycles does it take to prove a cycle? So trying to compare apples to apples. And in the future, I mean, there's a lot of companies working on hardware acceleration and so forth, right? At some point, we may sort of like go to using physics terminology to measure something like, you know, how much energy do you spend per proved cycle, for instance. So we are at sort of like an interesting phase right now where we have these proofs that while they're efficient to verify and they're efficient to copy and transmit, they're really expensive to create, right? And the question is, who's willing to pay for that? Okay, and it's very nice, I think, zero-knowledge proofs have been fortunate to meet the blockchain space because there are actually a lot of applications where we're willing to pay for that in the blockchain space, right? And that could be because it unlocks a unique capability. It could also just be because there's so much replication going on when you're verifying computation, right? So think about thousands of validator nodes that have to redo the exact same computation to verify that it's okay on a blockchain, right? Well, instead of doing that, why don't we just send a proof along that's very easy to verify that, hey, this is a correct next block. And also, the cost of storage is something that can be prohibitive on a blockchain, right? So instead of storing a lot of data and so forth, now maybe we can just have a proof that says, oh, there is some data that would result in this end state. So one of those examples, right, are ZK rollups, right, where It used to be that you do on-chain execution, so you have this kind of like low throughput, expensive operation whenever you're processing transactions. And now we're talking about, well, why don't we do all of that off-chain, right? And we just compute what is the delta, what is the change that would happen to the smart contract from all of these transactions, and then create a proof that that's the case. And then we just give the change and the proof to the smart contract, and it can update the balance. Okay, so the next thing I want to talk about is composability. So how do these things glue together? And here, it's really the succinctness property, why we like snarks, right? Because they ensure that these recursive proofs of proofs of proofs and proofs that you have when you do proof-carrying data and you're computing new data based on verifiable inputs, that they stay small, right? Because all of these proofs are small, and whenever, regardless of how many inputs and so forth you have when you're computing a new piece of data, you can still compute a small succinct proof for that being a correct operation. So the nice thing about snarks is that they compose well, right? They're succinct, so there's no size explosion in the proofs. They're non-interactive, so you can sort of like give them as inputs and be used in further computation. And the soundness of them is, well, cryptographically speaking, close to 100%. So also there's no degradation. It's not like you are getting sort of 9% and then you have another 10% loss in the next step and so forth, right? You're staying close to 100% soundness. And this is unlike other types of evidence you could give, right? So for instance, if you want to do direct recomputation to verify something, well, then you would have to send all the data along, right? So there would be no succinctness anymore. Right? If you wanted to do some interactive techniques, so like interactive proofs or spot checking or something like that, well, there's some interaction. You can't do recursion. You can't give that as an input to the next step. And for economic security techniques, which I think is a really cool idea, right? But it becomes difficult to manage this kind of economic security and track that over a long path of statements. One thing that's interesting about this proof cost, then when we use it in proof-carrying data, is that we can amortize the cost over many verifications. Right? So if you have a proof that you've created at some step, and then you're building on that, and you're building on that, and building on that, somehow you're accruing value of verification value in all these subsequent steps, right, that are relying on that proof. And I think this is sort of like a really sort of like nice thing, right? But it also points to sort of like maybe there's a threshold effect, that the more data we put into a proof-carrying data system, right, the more we can amortize the cost of creating a proof over many steps. Okay, so the last part I want to talk about are trust anchors and trust management. And in blockchain, we have the oracle problem, right? How can we get data into a blockchain? And the same thing happens with these proof-carrying data, right? Sometimes there are data that comes from outside, and we just have to trust them. Okay, and how do we incorporate those? And that's what I refer to as trust anchors, right? So there's a question of how do we incorporate that data? So maybe it's a camera that signs a raw image, it's Ethereum that finalizes block, and you have some sort of like threshold signature, multi-signature on it, or something like that, right? And this is an adoption barrier. So there are not many places in the world today where we get these trust anchors for free. People have to go around hunt for it. But the exciting thing, people are going around and hunting for it and trying to strip data from passports and using that for identification protocols and so forth. It does point to a problem as well, though, right? Which is proof management. What happens if a trust anchor fails? Okay, now you create a lot of data on top of that. You have proofs, right? And maybe you've lost, so like, what was the origin of that? So what if it turns out that, well, somebody who signed something, they're actually malicious and they signed some fake input? So I think there are lots of these kind of management issues that we still have to resolve with zero knowledge proofs and proof carrying data. And I think that's sort of like going to be something people are not thinking too much about now, but I think in the years to come, that's going to be an issue that is increasing in importance. Okay, so I want to wrap up. I've sort of like talked about some of the barriers I see and sort of like where we're going, and I'm hopeful that we're going to get there. So what is the end result? What does success look like? I think in the blockchain space, we're talking about the proof singularity. So think about taking all the computation and taking that off-chain and doing it where it's cheap, outside the chain, and really using sort of like the L1 chain as a verification settlement layer, right? Because that's what the blockchain is good at. It's good at verifying stuff. And more broadly, I hope we will sort of like be able to go sort of like beyond the blockchain space, or maybe we can hope for the blockchain space becoming sort of like all-encompassing is something that's very widespread in use. And there, the vision I'm hoping for is sort of like a digital world where we have this web of verifiable data, right? And since verification is cheap, right, hopefully people would want most of their data to come with proofs of correctness, right? And we will have a much more trustworthy world. And with that, thank you for your attention.
All right, thank you, Jens. We're actually running a short on time, but we can take some questions. Type theorists have thought a lot about composition of proofs. How can type theory help with composability of cryptographic proofs?
Okay, yeah. I'm not entirely sure, okay? So, but I think, I guess I suppose it's been from a somewhat different angle that type theorists have been thinking about this, I guess in terms of like, so one thing that you're using type theory for is sort of like static analysis, like so will a program execute correctly? Will it process the data correctly? And that is an orthogonal thing to what we are trying to do with these kind of proofs, which is more like, has it executed correctly? So in some sense, I think that is sort of like a complementary thing, and I think one should do both, right? So you should use sort of like formula verification in type theory to make sure that whatever you're doing is correct. And maybe for proof carrying data, there's also a question of like, how does one computation carry on from the next one, and does that make sense? And then you would want the proofs to make sure that, well, once you know that that is sort of like the correct structure of data and computation, then that has actually been executed correctly.
What are the advantages of elliptic curve-based proofs versus small field proofs?
Yeah, so I think elliptic curve proofs are, I think in some ways, easier to reason about. You can have some very nice homomorphic commitment schemes like Peterson commitments. The disadvantage is that you're working with larger fields, and that can be a costlier operation. So if I had to conjecture, I think the world is moving toward using small fields rather than elliptic curves, just for performance reasons, and then potentially also for post-quantum security.
All right, and a lot of people want to see this answered. Should we be prioritizing post-quantum proof systems?
Yeah. So I think it's not as urgent for proof systems as it is for, say, encryption schemes, because the proof systems, if there's zero knowledge proof, they're succinct, they don't actually carry the data around, right? So it's more a question of like, how long time do you want the verification to hold, and nobody could break the soundness. But for anything you verify here today, right, then since, as far as we know, no quantum computers exist, that should be good enough. I do think that the world is probably moving towards post-quantum security anyway, just because of like, they seem to be pretty efficient techniques anyway for creating proofs.
What proving system does Nexus use? Yeah,
so we have several proof systems. So we have a CKVM. We've re-implemented the NOVA family of folding schemes from the ground up. So that's NOVA and Supernova and Hypernova we have in the CKVM. But we also have an implementation of JOLT in the CKVM.
All right, given the time constraint, I think we can only take one more. What's an application of this verifiable layer you would be excited for that isn't currently possible?
Yeah, so I'm very concerned about deepfakes and in general, so like the news that you get and the fake information you get, and misinformation, which is very deliberate misinformation that we're facing. So I would love to have a system by which you had much stronger guarantees whenever you were reading an article or piece of news that, you know, that there's sort of like a path back to the original sources that provided that information. I've sort of like tried myself, talking to journalists being misquoted, not maliciously. It's even worse if it's malicious. So if there's some sort of like way of saying, you know, in an article, guaranteeing, well, that the original person who they talked to agree that this is a correct interpretation and so forth, I think we could already eliminate a lot of misinformation. And I think this zero knowledge proofs can be part of that. I also think that there are other components involved in getting to that solution.
All right, so unfortunately our time is up, but thank you so much for the amazing talk, Jens.